So, good morning everyone, and thank you very much for joining me today for my talk, Video Coding for Video Streaming. A few words about myself, that my research interests, as you can see from the word cloud taken from my Google Scholar, is mainly on video coding, video streaming, and also quality of experience. Currently, I'm holding a tenure track position at ITech, University of Colloquium. Before, I was a postdoctoral researcher at Athena for 3 years, and I got my PhD in 2022. I have 1 master's degree in electrical engineering and 2 bachelor degrees in biomedical engineering and electrical engineering, and I'm co-author of more than 100 papers and patents. In this talk, I will start to give a brief introduction about video streaming and video coding. Then I will talk about video coding solutions for HTTP adaptive streaming. Then the next topic that I will cover is the visual complexity analysis. Finally, I will go beyond 2D video streaming, just a few slides about our latest work, and finally I will give a future research directions. Why video streaming? As you can see here from the survey that taken from March 2025, we can see that streaming right now is having the largest share of the TV viewing. This survey has been conducted in US, and as you can see, streaming, for example, when we are watching the video online through a streaming platform, for example, Netflix, YouTube, Disney, Prime Video, etc., reaches to 44%, and the trend is that we expect that this will be increasing very soon. I expect that in the upcoming years we will reach to 60–70% of the TV viewing through the streaming services. But how does this work? Each streaming service has 3 main components: the server side, network side, and player side. Server is mainly responsible to encode the video and prepare the video for streaming. Network is mainly responsible to transfer the data from the server side to the client side. For example, when you are watching a Netflix video, the videos are in the Netflix server, encoded and prepared for the streaming. When you request a video through the internet, this video is transmitted to your device, and here your device is responsible to decode the video and play back the video. But one important aspect in video streaming is that we don't encode the video only once. We encode at multiple representations. These representations are the same video, encoded at different qualities and at different bitrates. So client, based on their device capabilities and also internet connection and available bandwidth, they choose the most appropriate representation and decode and play the video. My research interests mainly focus on the server side and video coding solution for HTTP adaptive streaming. But how we do this, there are multiple video codecs. The most successful and widely used codec is AVC, which was finalized in 2003 in MPEG and JVIC. They continue to have the next generation of the video codecs, HEVC, 10 years later in 2013. They could reduce around 50% bitrate for the same quality compared to AVC, but the latest standard is VVC that was finalized in 2020. Actually, I was there in the latest JVIC meeting before COVID. So they finalized this in 2020, and they reached again around 50% bitrate reduction compared to HEVC. What does this mean for us? Just as an example, for the same visual quality when we are watching a movie, if AVC requires 12 megabit per second to reach to this certain quality, HEVC will require only 6 megabit per second. So the file size reduces around 50%. And this is even more for the VVC that reaches around 3 megabit per second. So the size of the file is reduced as we are going toward the newer codecs, because they are using more sophisticated tools for the encoding. But they didn't stop here. There are currently lots of activities in JVET, in MPEG. They try to have the next generation of video codec. So it is expected that next generation will come 2027 or 2028. But main focus here is on the AI-based or learning-based codecs. So we categorize learning-based methods into 2 categories. One is end-to-end, fully deep neural networks. For example, autoencoders are used to encode the videos. But the second category try to keep the structure of a traditional video codec. So they don't touch it, but they try to replace some of the components with learning-based methods and improve the quality of the video codecs. Last week with some of our colleagues, actually we were in PCS in Aachen, which is about the picture coding symposium. And there was a keynote that's showing here that recent work reached better performance using the learning-based methods compared to VVC. So for VVC, we have the research activity and the company's activities around 40 years. In 2-3 years, some student in some university could surpass the VVC. This is 70%, but I know some papers even reported around 50% in just 2-3 years. And it shows the power of the AI-based video codecs. What does this mean to us? If with VVC we reach to 3 megabit per second, with the learning-based methods we can reach to 2.5 megabit per second, and in some scenarios even below 2 megabit per second, 1.5 megabit per second, etc. But there is a big but here. What is the problem? The next slide shows us. The decoding complexity of all of this method is very high. If we consider the decoding complexity of VVC is here, still we cannot run VVC in real time on CPUs for 4K 60 frames per second. And this is logarithmic scale. And consider the recent methods are 1,000 times more complex than VVC. And this explains why still a standard from 2003 is widely used. AVC, more or less all the videos are encoded in AVC. Just recently, the trend increased to use a bit more HEVC and AV1. And this motivates me to work on video coding for video streaming. So I see the video codecs as a black box. I don't try to improve the video codecs, but I try to choose encoding parameters for the existing codecs to improve the efficiency of the video streaming and quality of experience. So how we do this one? As I mentioned before, in video streaming, we encode the videos at multiple representation, multiple qualities, multiple bit rates. And if you look at your YouTube player, you can easily see different qualities, right? You can choose between each of these qualities. The higher the quality, the higher the size of the video that you are downloading. But some of the videos may have even more representations. So the research question that I try to answer is that what should be the efficient number of the representation? Do we need 5, 10, 20? And what would be their bit rates and their encoding parameters, for example, resolution, frame rate, and etc. I start with a practical example. For the Winter Olympics that started in 2010 for streaming, only 6 representations used for encoding, with the maximum bitrate of 3.4 megabit per second. 4 years later, in 2014, the number of representations increased to 7 representations, with the maximum bitrate still kept 3.4 megabit per second. But in 2018, we had 10 representations and maximum bitrate reached to 18 megabit per second and maximum resolution reached to 4K. But this is fixed bitrate ladder. What does it mean? That whatever that comes, doesn't matter it is animation, it is sport, it is movie, they are all encoded at these representations. This is very simple, right? So we don't do any kind of optimization, but it is suboptimal. Why it is suboptimal? Because we don't consider the content dependency. For example, if we have animation, maybe at this bitrate we reach to very high quality and we don't need any more all of these representations. What is the network dependency? Imagine that we are delivering these videos to a rural areas that they don't have the maximum bandwidth more than, for example, 5 megabit per second. Why we need to deliver these representations? So considering all of this, we started to work on this, and one of the first solutions is the network-aware bitrate ladder construction methods. The main idea here is that what we do is that we try to collect the information, available bandwidth from our clients. And then we are having the probability model against the bandwidth. These are the number of the requests from the clients. We see that mostly clients try to request the bitrates in these areas. Right? We don't have too much requests between 8 to 12 megabits per second. So based on this probability, we choose the bit rates to construct a ladder in a way that we try to serve the clients very close to their desired bit rate. And based on this, we construct our bitrate ladder. So imagine there is a request, for example, 1.2 megabits per second. We serve this with 1 megabit per second. In this way, we try to reduce the difference between the requested bitrate and the served bitrate that is constructed using the bitrate ladders. But the next approach that we consider is quality aware. So not only we consider the network and the request from the clients, we also consider the content itself. So if we encode one video at this bit rates and we then calculate their qualities from 0 to 100, we can see that lots of representations having very similar qualities. This video that has been encoded at 18 megabits per second has the quality of 98, very high quality. The next representation here has 12.2 megabits per second, but has the quality of 97. Is there any difference between them? We cannot perceive the differences. So why do we need to encode the video at both bit rates? We can simply remove this bit rate and encode at 12 megabits per second. So in this way, we try to remove perceptually similar representation from our ladder. We make it smaller and the cost of delivery is reduced. So here, as you can see, we construct a ladder by removing the similar quality representations, and we are keeping only those that having perceptual difference between them. And we use the JND aware bitrate ladder construction method when there is a perceptual gap between the quality of the representation. And in this way, we could publish some papers and we could reduce around 30% the delivery bitrate from server side to the client side. But the question here is that what should be the difference between quality of two representation that human can perceive the differences, right? If the first representation has quality of 98, what should be the quality of next representation that we see the differences in qualities? Netflix says it should be 6. So if the quality of first representation is 98, the next one should be 92 that human can perceive the differences. And anything between them is similar quality, having a similar qualities. But there is another study shows that this difference should be 2. So this motivated us to start to work on this. And we saw that it is completely content dependent. There is not a fixed number that we can rely on. So some of the contents having the quality difference of, for example, around 1, 2, but some of the content, even with quality difference around 15, we cannot perceive the differences between them. So based on this, we started to work to address the content dependency. We published around 10 papers on this. So first we started to extract some handcrafted features and then using the machine learning methods to address this issue. But also we could reach to the state-of-the-art method. And I think 2 weeks ago in VSIP that we organized in Colloquium, we also proposed a new method that uses the deep learning methods, in particular very simple CNN and then LSTM, on top of the handcrafted features to improve the efficiency of our method. And again, we could even improve the state of the art for this method. But later on, we were the first that we proposed how to compute the confidence interval for the quality differences between two representation. And for this one, we could get the best paper award from PCS24, and then we could extend this work to paper and transactions on image processing. I don't go into the details because it has lots of mathematics, but if you are interested, you can find in the paper. But the next question that we started to answer is that how we can encode a video at a certain quality. Now we are not interested in encoding videos at a certain bit rates, then we don't need rate controller. We need now quality controller. So imagine that I want to encode a video at quality of 95 and the next would be quality of, for example, 90. How I can modify my codec that we can reach to certain quality. For this, we started to work in a method that we call it deep QC, deep quality controller. So our method has two different approaches. The first one is that we simply extract the handcrafted features, spatial temporal complexity features, but also we use clip to extract the semantic information. And altogether, we try to predict a QP that we know that if we encode video at this certain QP, we will reach to a target we have, to the target quality that we have. We submitted to ICASP and recently we got the reviews, very positive reviews, and we hope that this will be published. So our approach reaches to target quality with a very minimal error. So the error in the quality is around 0.5. So now that we know using the network-aware solutions or quality-aware solution, we can find the optimal number of representation and their bit rates. What else we can predict to improve the quality of the video stream? In addition to the predicting the number of the representation, that should be 12, 5, 6, whatever, and their bit rates. The next thing that we consider is the resolution. Right? For each video that encoded at these bit rates, we can find the best resolution. And why it is like this? Because if you see here, if we encode one certain video at multiple bit rates and at different resolutions, and if we look at their quality, we can see that the best quality for this video happening at Full HD or 1080p. This is a simple video. But if we look at a complex video, we can see that the best resolution happens at completely different resolutions. So finding the best resolution for encoding is completely content dependent. For different contents, the best resolution for encoding varies and is completely different compared to other. So motivated by this, we try to find the best resolution for encoding, and we show that around 30% bitrate reduction we can achieve simply by predicting the best resolution for encoding. So just think about this, that new standards, it takes 10 years to reach 50% bitrate reduction, but simply by finding the best resolution for encoding, we can reach around 30% bitrate reduction. But what else compared to resolution? The next that we consider is the frame rate. We don't need to encode all the videos as a fixed frame rate. Just giving you one example here. If we want to reduce the frame rate of these two videos, there is a lady here is just reading a book. It's a bit stationary, but the other one not only has the camera movement, but the person is running. Which one do you think will be more affected if we reduce the frame rate? Right. You can see the jerkiness, but it doesn't impact the second one, right? So we can see that we can find the best frame rate also for encoding, because if we reduce the frame rate for encoding, the compression efficiency will be increased, the encoding time will be reduced, because instead of encoding 60 frames per second, we are encoding only 15 or 30 frames per second. Decoding complexity will be reduced, because instead of decoding 60 frames per second, we are decoding only 30 or 15 frames per second. So in this way, we can enhance the efficiency of our video streaming. So we propose PSDR, per title encoding, using spatial temporal resolutions, and we could increase the compression efficiency by simply selecting the best frame rate for streaming. What else? Any idea? The next that we consider is the energy consumption. So we try to choose the resolutions and frame rates in a way that we could reduce energy consumption not only at the server side, but also at the client side and device side. So when you're watching a video, if you use our solution, your battery will be alive maybe 30% more, but the quality drop will not be noticeable. We worked a lot on this topic. Because we had too many contributions, I just simply skipped this in the interest of time. But we could publish one of our papers in JetCast was the Spotlight paper. We got Best Paper Award from NAB, and our other paper got selected as the Best Paper candidate in VCIP 2024. But we can discuss this if you are interested later in Q&A. The other topic that we consider when we are constructing the bitrate ladder, how we can address both CPU users and GPU users. We know that deep learning methods can enhance the quality of images and videos, right? But they need GPUs. But not all the devices have GPUs, right? So how we can address this scalability? What we do is that we construct a bitrate ladder. As per usual, we assume that all of the devices having only CPUs. Then, per representation, we train a deep neural network specifically for this video that can enhance the quality of this video and make it more similar to uncompressed video. That's perfect, right? So we have a deep neural network that can enhance specifically our video and the quality of this representation. But what is the problem? This has been trained for this video. So we need to transmit this deep neural network as well, right? So we will have the bitrate overhead. How we can solve this? We try also compress this deep neural network. So we reduce around 80% the size of this deep neural network. And we add this compressed deep neural network as a metadata to our bitrate ladder. Then when there is a request from a CPU user, per usual, we just transmit the video stream. Nothing has been changed. So if you have still the CPU user, got the same video as before and decode it and play it. But when there is a request from a user that not only has CPU but also GPU, we not only transmit the video, but also a metadata. And this metadata is used to enhance the quality of the video for the GPU users. And in this way, we could see that quality of video for the GPU users significantly enhances. We reach around 11 quality enhancement in terms of the VMAP for GPU users. With very simple method, our deep neural network can be run real time on the GPUs. But there is another problem. Training costs can be high because we need to train a deep neural network per video, right? So because these are content-aware deep neural network. So we started to work on this and reduce the complexity of the training. As you can see, usually we use all of the patches from all the frames for training this deep neural network for this specific content. But we thought about this actually, we did this work with Ying, that all our patches informative and important for training. The answer is no. We have only a few number of the patches that are informative for training. Then through some algorithms, by finding the spatial complexity of the patches, we use only those that having lots of details. And if they are simple, we don't care about them. Also, we compute the temporal complexity because if there is no motion in a patch, which means that that patch is very similar to previous frame, why we need to add it again to our training pipeline. In this way, we select only a few number of the patches for training. And we could reduce up to 96% number of the patches that is needed for training. It is significant, right? Only with 4% of patches, we can achieve the same quality as if we use all the patches for training. And as you can see here, if you look at the quality, if we don't use any learning-based method and only bicubic, the quality look like this. But if we use our method, which has been trained for this specific video, you can see that the quality is more similar to the ground truth quality. We again continued this work in another work, so I don't cover that one. So I'm moving to another work, that if we have GPU, how we can enhance the quality. What are the solutions? Video enhancement methods can be used, for example, super resolution. But here we started to work on the video interpolation. As you can see, if we have an original video and interpolate the videos, it looks more smooth. The quality is much better than. How we do this? Using the interpolation methods, right? But recently, generative AI is widely used, right? So we started to see if the gap between the first frame and the last frame is high. For example, there is 24 frames we want to interpolate. How generative AI works? And you think that it's not that much promising, right? So we worked on this idea here. We try here to use the text information. We extract the text from the first frame and the last frame. And we use this semantic information plus some flow estimation methods together to guide our diffusion model to generate better videos for us. Right? So it is dual guided framework, one using the flow estimation method and one using the semantic information. And we reached here to the state of the art. So we are now even better than the latest CVPR papers. And as you can see our result, if this is the first frame, 6 frame, 12, 18, and the last frame that we use, we try to interpolate all of this frame. As you can see, the state-of-the-art method cannot reach to interpolate the original frame. Right? But our generated frame is more closer to the ground truth method. So in this way, we try to enhance the quality of the interpolated method. As you can see, we reached to the state-of-the-art, and for example, this reference 11 was published in CVPR 25. So moving forward from the bitrate ladder construction methods, I am moving to the visual content complexity analysis. Right? Which of this content is more complex? Right. We have here not only the spatial complexity, lots of details, but also we have the temporal complexity because we have the camera movement. Here we don't have camera movement, and the background is super simple, right? So one of the research that we started to work is that how we can determine the complexity of the visual content. Why it is important? Because if we could determine very fast the complexity of the videos, we can use it for the video coding purposes, for the encoding parameter predictions. We can use it for visual quality assessment, content selection for some subjective tests. We can find and determine some busy areas, complex area to hide the data. So for interactive image segmentation and many other applications that you can use this. One example that I am showing here is that when we want to find our bitrate ladder and find our best resolution for encoding, if you remember, one of the tests that we did is that when we want to encode the video, we want to find the best resolution for each of these bitrates. One solution is brute force. We try all the resolution and find the best, but it's very expensive because we need to encode multiple times to find the best one. But if we could extract some features here very fast, we can use these features to predict the best resolution and best frame rate and whatever we want, right? So here in a demo in NAB, we showed this. And here you can see that if we encode the same video at 2 different resolutions, 1080p and 540p, but at the same bitrate, right? You can see that the 540p here works better. They have the same size, but they have been encoded at different resolution. But this video have better quality compared to other ones. So we use actually this visual complexity features to predict the best resolution. But later also we use to predict the best frame rate, etc., etc. How we do this? We started to use the one standard which is called SITI, Spatial Information and Temporal Information. What they do is that in the video, they find only the edges of the objects. And they say that if the number of edges is huge, that image is more complex, right? But we show that this is not very well correlated with what we want to predict. So we introduce actually VCA or video complexity analysis that we use the DCT transformation to find the complexity of the videos, right? So if a block is more complex, it has more high frequency data. So in this way, we find the more complex videos for both spatial complexity and temporal complexity. But later we extended this work. Actually, we re-implemented this work. This has been done on a CPU, But later we also wrote it in Python that if you have a GPU, you can also use this method to predict the spatial complexity and temporal complexity of the video. As you can see, compared to the state of the art, we reach more or less the same speed. We can extract a feature around, 1,200 frames, features for 1,200 frames. So it is completely real time, super fast. And as you can see, our method in terms of the spatial complexity and temporal complexity works much better than state of the art. But later we thought, okay, we are not old people just working only on the signal processing. So let's also see how does AI-based method works here, right? So what we tried to use is that instead of using unsupervised method, we tried to use the supervised method. This was the motivation that we introduced deep VCA. So for deep VCA, as you can see, we fine-tune a deep neural network, for example, EfficientNet, ResNet, whatever, to predict the spatial complexity, the detail into one frame. This is used for all the frames. And then we extract the latent features and we compute the similarity of latent features. And then we use it as a temporal complexity to see how much two frames are similar to each other. If they are very similar to each other, which means that we don't have any temporal complexity, we don't have any movement in the video, right? But if the latent features are not similar to each other, means that we have huge temporal complexity. As you can see here, from somewhere in the network, we extract the features, latent features, and then we concat them and we compute the similarity of the features to predict the temporal complexity. And our results show that in particular for temporal complexity, from state of the art, the correlation is around 46%, we reach around 84%, a huge, huge improvement compared to that one. So just to summarize our activity here, we introduced VCA, which is mainly based on can be run on the CPU, but more recently, Mikita is here, he could also implement it in FFmpeg. So the speed is a bit larger, better compared to the original VCA, and also it can be used on all the platforms. Mac, because before we had problem to run it on ARM and Mac, but right now with FFmpeg you can run it on all the devices, but also we extended to compute the complexity of the stereoscopic videos that I didn't mention it here. We had eVCA, this is mainly on the GPU, and deep VCA is also mainly the GPU. But thinking about the visual complexity, we cannot ignore the semantic information, right? Here you can see that if we extract the text from these videos, we can use the semantic information to better predict the complexity of one image. Here, you can see some examples. We extract the text from image. We have this image, and this is the corresponding text extracted using the image to text module, right? So this is the second one, and this is the third one. We can get lots of semantic information. For example, motion. You can see those that are highlighted in blue, they are showing the motions here. We may have culture and American flag, right? So we can get many actually semantic information, mood, for example, position. It is on a field, in front of whatever. So we use this text information to enhance the prediction. And here you can see that our framework using the semantic information reaches to the state of the art, and we could publish this in BMVC, British Machine Vision Conference this year. But the other one that I'm very much interested in is that considering the implicit motion. If you look at the psychology, you can see that some of the static image, I'm not talking about the videos, I'm talking about the static image. People may perceive implicit motion for some of the static images. When you look at this, what do you perceive? Let me see if I can. Something like this, right? It doesn't, the picture is static, but we have an implicit perception of the motion here, right? For the other one, our brain may think something like this. And for the other one, we may think something like this. This motivated us to use some image to video generation methods. So what we do is that from each image, we extract the text, and we use this text plus this image to generate a video. Now we have three modalities. We have video, generated video, it's not a real video. We have the text that we extracted from the image, and we have the image itself as our input. And then we extract feature from all of this multimodal actually inputs, and then we try to predict the complexity of method. And again, we reach to the state of the art here as well, so we could improve the prediction of the complexity. So we had some ablation studies, so we tried different image to text methods. We don't see a big difference. We try to have an ablation study for, on the different image to video methods. You can see that we may generate different videos, but the result doesn't change, don't change that much. So I promised to be 40 minutes, so I'm having just few slides at the end. We moved beyond 2D. So we are not only working on the 2D video streaming. So we started to work in particular on the stereoscopic video streaming. We collected the data set. So we have some studies using, for example, the Apple Vision Pro for the dart gaming. We started again Apple Vision Pro for another game. Then we also studied the depth perception of Apple Vision Pro. We have some learning methods. Just recently we submitted that how we can evaluate quality of the stereoscopic methods. For my future work, I will focus more on the immersive video delivery. I will work specifically on the holographic image compression and delivery. I will try to use more generative AI for video coding application, and I will focus on sustainable quality assessment of the video streaming. And the last slide is mainly on the advertisement. So if you are working on the quality of experience, please consider submitting a paper to QMAX. The deadline would be around February for the full paper, but for the short paper, we have the deadline of April. And thank you very much for your listening.